Hey folks, just wanted to check a couple of minutes before we join in. Just give me a sec. I just wanted to see if everything is working as expected. Yeah. So yeah, I see everything to be working good. No major issues. Just a second, folks. Just a quick message and then I'm here. Okay, sounds good. I'm just checking if there is any problem from any one of our team members. So this seems to be working perfectly okay. So I'll close this app of ours. So I'm back live now. So yeah, I hope everybody can see me. Just quick check around. Just quickly. Okay. I'll close. Okay, so everything seems to be good. No hiccups whatsoever. Okay, so we're live. It's 10 sharp AM Indian Standard Time, and yeah, let's get going. But I would recommend that we wait for a couple of minutes. Let others join in. Maybe we'll start in 3-4 minutes. So yeah, for today's discussion, we would be using the Slack. On Slack, we have a channel called Miscellaneous. So let's use that channel for all comments. And I mean, because that way it's easier for me to track where all the comments are. My team is also looking into some of the comments. All the most interesting and upvoted comments or messages on Slack would be sent to me via WhatsApp, so that even if I miss something, if I'm misreading something, we have our teammates helping us here. So, okay, where are we? So let me just open Slack also. Okay, so yes, I'm also checking the miscellaneous section here. So everything seems to be okay. No major issues from my side. The streaming seems to work perfectly. Let me also check on my mobile phone. Yeah, so everything seems to be okay from my end. Yeah, so no major issues whatsoever. Check on my Okay, yeah, everything seems to be going good. Okay, no speed issues. I just checked the speed issues also, just to make sure that we don't have hiccups while we are doing it. Okay, folks. Yeah, anything? So if you want me to speak for a while about some topic that might interest you, just put it in the miscellaneous channel of Slack. I would take. Since we'll wait for a couple of minutes for everyone to join, I could probably answer a question or two. So. Or somebody was asking about the website. We already have the new website already working, but we had small issues while porting all of the data from the old website to the new website. So we just don't want to lose any comments or any old data. So just give us maybe a few more days, and we should have it ready. We are just ensuring that there are no major bugs when we move from the old website to the new website, and hence we are and hence we are still waiting to roll it out. So yeah. No. So once the validity of the course is over, you'll not be able to access the live sessions, and you'll not be able to access the course content also. So that's one of the questions that was asked. So applications of machine learning in defense, of course, there are tons of companies, from Raytheon in the US to large Israeli companies, which are working on machine learning and AI in defense forces, especially related to surveillance. For example, I think the Israeli government has a huge surveillance infrastructure across the wall that they have between Palestine and Israel, where they would track people also, and that's one application in surveillance. Also, there is a lot of satellite imagery that most defense satellites end up capturing. There is a lot of visual analysis of this satellite imagery that is typically done at scale, because they're literally scanning a large portion of the world with this. So certainly lot of applications of machine learning in defense. It's just that we don't hear about it a lot. For example, some of you may know about this company called Roomba, which is a very popular robotics company by Rodney Brooks at MIT. So that company makes this room cleaner, so which is like a very nice device which can sweep rooms. So Roomba also has a huge military division where it builds robots, intelligent robots, for the US military and for militaries across the world. So of course there is intersection of robotics, aviation, and surveillance and security and things like that, especially for defense forces. So so somebody was asking about big data. We'll discuss this for 2 hours, so don't worry. So I'll give you a lot of brief about big data. So yeah, reinforcement learning. Somebody is asking about reinforcement learning for gaming. That's the thing today, right? For many games like chess, Go, you name it. Reinforcement learning is the best way that we know today to solve some of these really hard problems. Uh, yeah, so somebody is asking about using Google Cloud Platform. Of course, you need credit for this. Nobody can give you compute for free. It's almost impossible because Google invests probably millions or even billions of dollars on this infrastructure. They need, I mean, they can't give you this for free, unfortunately, because these are actual physical boxes and compute resources and electricity that is consumed. So if you want to use any cloud computing infrastructure, you need credit. You need to pay for it, unfortunately. It's not free like Google search. Even Google search is not free if you think about it, because it's the advertisers who pay Google for those advertisements, which because of which Google is free. So yeah. So somebody was asking about how Apache Spark is related to machine learning. We'll go to that. We'll go to those questions in this session. By the end of this session, you will have answers to many of those questions. So somebody was asking about job assistance provided by you is limited to which cities. We don't have any limitation as long as we have recruiting partners in various places. We try to accommodate all the cities that we have. We have people who have hired in almost all the major cities in India. So from Noida to Chennai. So of course, it will most likely be a tech hub. If you ask me for a machine learning role in a tier 2 or a tier 3 city, of course there are no roles and we can't help you there. But we recommend that you look for, or you be available to move to positions which are in major cities where there are more openings present. So we cannot guarantee you the city, by the way. Okay, sounds good. So let's get going in this. Okay, so there are a lot of comments here. I'll not be able to answer all of them. And without any delay, let's go into the live session itself. So yeah, I'll move from my screen to a notes that I've written. I'll share this Google Doc with you at the end of the session on the miscellaneous channel of our Slack group. So this is just notes so that you don't have to write notes or you don't have to remember URLs. I'll keep updating any URLs that I have. So let's go into this. Okay, share. I'm just sharing my screen. Let's go into the screen share mode. Okay, this looks good. So yeah, I'll keep using my my regular pointing devices that you know of. So yeah, so this session is called Introduction to Big Data and Big Data, especially for machine learning and deep learning applications. Again, let's be honest here, it's almost impossible. Big data is a full course in itself. This would be close to like a 150 to 200-hour course, right? Unfortunately, we don't have bandwidth to focus on other courses right now, and hence we are not doing the big data course. But certainly at some point, because some students have asked us for it, certainly at some point in the future, we would love to do it, because this is a topic that I personally love a lot. And I've used it extensively myself. So what we'll do is we'll give you an overview of everything so that you understand what each of the major terms in big data are, because we keep getting asked this question: what is big data? What is Hadoop? What is Spark? What is MySQL? Tons of questions. So what I'll do here is I'll give you a historical perspective. I will try to motivate you with a historical perspective on how most a historical perspective on why we have so many tools. So in this session, we will try and answer the why instead of the what, right? So what is Hadoop? How does Hadoop work internally? We'll not be able to answer them because that takes a lot of time, but we'll give introduction on why we need Hadoop, or why did Hadoop come into existence in the first place, right? Or how Hadoop is used today to crunch large amounts of data, or how Spark is used, right? So in the introductory video, the 3-minute, 4-minute video that I sent you, again, let me give you a brief overview of what we do. So I'll give you a brief overview of what big data actually means, and what are all the tools that we have currently, and why do we need so many tools? Why are traditional databases, like in our course we have an SQL chapter, and the whole SQL chapter we learned using MySQL database, right? MySQL databases are called relational databases, right? We also discussed this in the course. These are called relational databases. because we have tables. They mostly process tabular data, right, with rows and columns of information. Okay, so these are called traditional databases or relational databases, like your Oracle's databases, your IBM DB2, MySQL, SQL Server, Oracle databases, etc. So we'll understand what is the problem with traditional databases, and what technological advances brought up all the new big data technologies. If you recall, big data technologies only became popular from around 2005 onwards, right? And I personally started using most of these big data technologies from 2009 onwards. For almost the last 10 years, I've been using most of these technologies myself. So big data technologies started off almost around 2005. They only became popular around 2010. And their popularity, there's so many tools right now, there are so many variations. We'll understand why each of those variations is needed, and why did this change come about, right? Why did this change? Because from almost the mid 70s, so from the mid 70s up to mid 2000s, we had traditional databases, and they served a very good purpose. They solved most of the problems that you had. Now, why did a sudden change happen? So we'll also look at, in general, how supercomputing or parallel processing was done earlier to 2004. Then we'll go into what Hadoop is, some advantages of Hadoop, when to use Hadoop, when not to use Hadoop, why did Hadoop come into existence, what technological changes brought about Hadoop in the first place. Then we'll move into Spark, on why Spark came into existence when we had Hadoop. We'll also move into, in general, deep learning, because we've discussed a little bit of graphics processors, GPUs, all of that stuff in the course also, in the introduction section to deep learning, and introduction section to how TensorFlow works. So we have some of this covered in the course, but I'll just repeat some of this and give you perspective on how large-scale deep learning models are built today using large GPU clusters. Then we'll transition into NoSQL databases, because at the end of the day, most of machine learning is about data storage, right? What all are the non-traditional databases? Like you have traditional databases, and what are the traditional MySQL, Oracle databases trying to do? And what are the new databases trying to achieve? And then we'll close out with a small introduction to cloud computing, like what is Google Cloud Platform, what is Amazon AWS, why are they there even in the first place? Why do we need them? And how to keep yourself up to date in this moving landscape. This is a very fast moving field today. Okay, sounds good. So let me just transition to this. Okay, so folks, anybody who has a problem with the desktop app, please give us a call to our phone number on our website. We'll try and resolve them as fast as possible, and we have resolved almost all the queries that came through us. So please do check your emails. We have sent multiple updates in every video that have done since we had an update and a key. I've been mentioning it. So please keep an eye for, if you just come and ask in the last minute, I don't think we can resolve all the questions in 5 minutes, right? So please, at least for the next live session, all of you, please have your pins and desktop apps working. Okay, sounds good. So let's get into the discussion. We'll start with what is big data to start with. Okay, so just give me a second. I just want to ensure that everything is working smoothly. Yes. Okay. So I hope everybody can see the screen, right? So the first question is, what is big data to start with? Of course, there is this Wikipedia page which will tell you what big data is all about. But in a nutshell, what has happened is, since the internet started, like since the early 2000s, the amount of data, the amount of data that we started collecting has increased enormously, primarily because of Google. Google is one of the primary reasons, because Google has been collecting, again, I shouldn't say only Google, but one of the reasons is Google, because Google literally processes, or literally tries to capture all of the information that's on the internet, so that it can make it available through search. So Google probably is one of the really big data applications and early big data applications. And of course, after that, you had Facebook, where people were willingly posting tons of information about themselves, images. There is petabytes of information that is being posted by people every day, or on regular basis on Facebook. Then you had all the social platforms, basically all of your social platforms. And of course, you also had your e-commerce platforms, right? E-commerce platforms, your movies platforms, your YouTube, right? All of these platforms, because they are web-based platforms, They could collect tons of data, which regular retailers could not. Imagine if I was Walmart earlier. Imagine if I was Walmart versus I was Amazon, right? Imagine this was in the year 2000, right? Amazon, because there are millions of customers coming to their web pages, they can track every action that the user has done on the website, right? They can track things like which web page did the user go to, and how much time did he spend on that web page, what product is he looking at, what product is he revisiting. All of this information Amazon could collect because it's an internet based company. While Walmart, because it was a offline retailer in around 2000, right, it collects some information like your payments information. Whenever you swipe your credit card or your Walmart card, it would collect some information, but it's certainly no way comparable to the data that Amazon or Google or Facebook or other e-commerce and movies and YouTube type companies were collecting. So one of the major developments that happened in the early 2000s, one of the major developments that happened is because of internet companies, and the whole massive adoption of internet and mobile. Of course, from around 2007, it's been because of smartphones and mobile phones that we have started collecting tons of data, far more data than we could ever imagine, right? So the speed at which we are collecting data has grown massively. Just 1 petabyte of data was unheard of in the early 2000s. That's almost unheard of. By the way, for those of you who don't know what is 1 petabyte, 1 petabyte is about 1,000 terabytes of data, right? We all know what a terabyte is, right? A terabyte is basically hard disks today. And even a 1 terabyte hard disk is unimaginable in the early 2000s. Even around 2007, 8, when I was doing my masters, 1 terabyte was like crazy large, right? We typically had systems with 2 GB RAM. 2 GB RAM was considered good. 4 GB was considered like great, right? Even in mid 2000s, forget about early 2000s, I think 512 MB RAM was considered good, right? So yeah, I have been programming, I think, since around 2001. Yeah, I have been programming since 2001, roughly, since my 11th grade, right? So since then I have been programming, and I've seen computers go from like tiny minuscule amount of hard disk, minuscule amount of RAM, to talking about, I mean, now I have a 1 terabyte desktop at home, and that's, I mean, multi-terabyte, not even 1 terabyte. I have 64 gigs of RAM. So all of that is possible today, and it's not super expensive. So what happened is, because of internet companies, that's one of the main reasons. Not just because of internet companies, but internet companies were the major reason that we started collecting large amounts of data. Of course, there are many ways of looking at this data. If you go to the Wikipedia article here, it talks about, okay, look at this turning point that happened. So we were collecting very small amounts of data till 2002. From 2002, the amount of data that we have started collecting even till 2007 is massive. So there is an explosion of information that we have collected, stored, processed since 2002. So this is typically referred to as the beginning of the digital age, right? So there are typically, people call 3 properties of big data. Of course, these things keep changing. Some of them are marketing gimmicks. So there is a large volume of data, there is a large variety of data, and there is a large velocity of data. What does velocity of data mean? Velocity of data means there is a large amount of data coming in per unit time. Imagine Google, right? I'm assuming there are millions of searches. I don't know. I'm assuming there are millions of searches per second or per minute at Google across the world, right? So there is a huge velocity of data because of large volume of data coming in very short amounts of time. There is a large variety of data, obviously. For example, if you're Amazon, you would get a lot of data, right? Not just purchase data. That's what Walmart always had, just purchase data. What Amazon could collect is your intent. Are you looking to buy a telephone, or are you looking to buy a mobile phone, or are you looking to buy a television? So it has a lot of huge variety of data. So these are the 3 properties that people initially started talking about, but there are 2 others which they added, called veracity and value. Veracity, basically, in a nutshell, is how much noise is in the data, right? If the data is too noisy, it's going to be less useful. Certainly there is value in the data. If you just have data and you can't make business value out of it, then it most certainly is not very useful, right? So there is also this whole thing about big data being the new oil. Certainly, if you have large amounts of data, and if there is value in the data, right, then you can mint millions of dollars through that. For example, just to give you a reference, on Amazon.com, you have these customers who bought this also bought, right? These are called product recommendations. These are called product recommendations. We also have a case study on this in our course, right? So if you look at product recommendations, publicly available data shows that almost roughly 1/3 of Amazon sales come because of these recommendations. And how did these recommendations come about? These recommendations were made possible because of looking at past customer data, because of past customer purchase data, right? And that contributes to literally 1/3 of Amazon's retail revenue, which is Amazon's retail revenue is a few $100 billion today, right? That's a massive amount of money. And of course, Amazon has great data, and they've leveraged this data to literally mint money by creating value to the customer, obviously, right? If you don't create value to your customer, nobody would come to your platform. Same thing with even YouTube, right? So today, YouTube has so many billions of minutes of content watched across the world every day that they can make phenomenal recommendations to you on what other videos you might like. They're sitting on a gold mine of data, thereby more people spending more time on YouTube, thereby YouTube enabling more users and providing more users with better content, and also minting a lot of money through advertising, right? So big data is all about these 5 V's today. Of course, some of this is marketing stuff, but in general, it makes sense. Volume of data, variety of data, velocity of data, veracity means how much noise is there, and of course, there is value in the data, right? If your data is not valuable, then it's not useful. Now, all of this, remember, I'll also give you timelines around this. So all of this became only majorly popular, started becoming popular in the early 2000s. But after 2007, after we started having the first iPhones and first smartphones, this data exploded. Now in after 2000, I think in 2020s, when IoT devices will become more popular, right? Basically, what is IoT device? IoT device is basically a sensor that you can place. It's basically a sensor you can place on any physical device or any device for that matter. For example, I wear a Fitbit watch. A Fitbit watch is a sensor sitting on my wrist, measuring my heart rate, measuring my sleep patterns, measuring my exercise, all of that stuff. So I can think of my Fitbit as an IoT sensor that I have. And we have a case study on analyzing the Fitbit data, right, in our course. So in 2020s, I think almost all the major machinery of the world will have sensors, which will measure things like temperature. Imagine I'm building a factory setup, right? I have a factory. If I can measure the temperature of all the critical equipment, the pressure, right, the vibrations, all of this information, if I can somehow measure them, I'm sitting on a gold mine of data, and I can predict when my machines might fail, or or whether my machines require some repairs, right? All of that I can do. So I think the amount of data that we're going to collect is only going to increase massively. There is going to be no reduction here. There's only going to be a massive increase. So today we're already sitting on a gold mine of data, but I think it will only explode in the near future. Okay, just a quick water break and I'll be back. Just a second. Okay, so big data in a nutshell is all about the major advances that have happened in data collection and the amount of data and the variety of data that we've been collecting since the early 2000s. That's what it is in a nutshell. Of course, the Wikipedia article gives you a lot of historical perspective and also lots of definitions, variations, all of that stuff, right? But here is a question, right? If you think about it, we had databases, right? We had databases for a long time. Databases are a critical component of modern computer science. Whether you're booking a railway ticket through IRCTC, or whether you're booking a flight ticket through any flight booking websites, whether you're booking appointments for your doctors or any movie tickets that you're booking, all of them use some database or other. For example, we use databases ourselves to store students' information. We use a MySQL database, right? So we use a MySQL database ourselves internally at Applied AI course, right? So databases are at the crux of it. But traditional databases like Oracle is a giant in this space. Oracle has a very well-known Oracle databases, series of Oracle databases. Then you had MySQL, which is a very popular open source database. And our SQL content in the course has been done using MySQL database, right? There are also other databases like PostgreSQL, PostgreSQL, right? There is obviously your IBM DB2, which is a very popular database. Then you have Microsoft SQL Server. All of them are traditional databases, right? Now, these traditional databases have been there from late 1970s onwards. If I'm not wrong, I think It was in the late 1970s, two mathematicians called Boy and Cord, right? So if you've studied computer science, you would study in databases courses called BCNF, Boy Cord Normal Form. If you don't know what that is, don't worry about it. Okay, so these two mathematicians came up with the mathematics needed for modern databases, and a bunch of companies, pioneering companies like Oracle, IBM, and Microsoft came up with databases, and databases were a terrific business. But the fact was, these databases, these traditional relational databases, that's very important. These traditional databases, they're also called as relational databases. They would store data in tables, right? You would have tables like this. For example, again, you have seen this in the SQL chapters of the course. For example, you would have things like, okay, each row may represent a student, right? Each column may represent the student ID, the student name, student email address, etc., etc. So this is basically called a tabular data, right? So most relational database, classical relational databases like Oracle's old databases, IBM DB2, they all were phenomenal when it came to store tabular data or relational data as it is referred to. And SQL was the most popular language, right? SQL was the most popular language to query the data that is there in the relational databases, right? So the fun part with these relational databases, what they were super powerful for almost 30 years, or at least 20 years for sure. For 20 years, they ruled the data world because they were the primary way in which people were storing data. Now, the fun thing that happened was when Google started, right, in late night, I think Google started in 98, if I'm not wrong. And when Google started Google was literally crawling the internet. Google was crawling the internet, and it was trying to store all of the information that it got on the internet into the databases. Then immediately these relational databases started failing because they never were designed for like petabyte scale data sets. They were not designed for petabyte scale data sets, right? I think the largest databases before Google were quite small, maybe a few terabytes at most, right? So these databases were only designed, by the time Google started in late 90s and early 2000s, most relational databases could not hold, like petabytes is like way hard for them. A petabyte is 1,000 terabytes. So most relational databases were capable of handling a few terabytes of data. The moment Google started crawling the internet, they were sitting on like on massive amounts of data, at least hundreds of terabytes of data. So Google, of course, is founded by brilliant, not machine learning, brilliant computer science PhD students, right? You have, and their initial team at Google were phenomenal computer science folks at Stanford. They were hardcore computer science guys. So they said, if the relational databases are not scaling, let's solve the problem ourselves by doing something hacky, right? So these are not working, but we are computer scientists. We know computer science as well as anybody. So why don't we solve the problem from a different angle altogether? Okay, so that became the basis of most of big data tools today. So your Hadoop and all these technologies came out of Google's initial research as well as implementation of custom systems to scale for petabyte scale data sets. Again, we'll come to the history of Hadoop and how Google contributed to that little later, right? So, but what was happening was, why the old tools did not work well because the amount of data generated became massive. Traditional databases did not scale well to new data sets, especially Google scale data sets. And people wanted cheap, scalable, and efficient ways to process this data. Imagine if you are an architect or if you are a software engineer at Google in the early 2000s or even late 90s. There is this phenomenal guy called Jeff Dean, who is now a Google fellow, one of the senior most software engineers at Google. I think he joined Google around that same time in late 90s and early 2000s. And he was instrumental in building most of the phenomenal infrastructure and great projects that Google has built, including TensorFlow. He's like the rock star of software engineering world. Probably one of the best software engineers at Google, to the best of my knowledge. Right? He has tons of research work that he publishes, a phenomenal guy. So Jeff Dean and many teams at Google, including their founders, they said, okay, what do we have now? Okay, of course, Google was a startup then. Google could not put in millions and millions of dollars into, so they were sitting on literally hundreds of terabytes or even petabytes of data. They said, how do we process this data? Because they need to process this data to be able to build a search engine. If they can't process all the data that they were crawling, they can't build a search engine, right? They said we have to do it cheap because we are a small startup. Back then, Google was a small startup, okay? They had to make it scalable because they knew that the internet was growing. They knew that internet was growing massively fast. So they wanted a system that they can easily scale, right? Imagine if I have hundreds of terabytes today, tomorrow if I have tens of petabytes. If I have tens of petabytes, I should be able to scale to tens of petabytes very easily. And of course, you want an efficient way to process this data. Google stumbled upon a very interesting idea. Anyway, we'll come to that when we learn about Mapreduce and things like that, right? So those are the reasons why the old monopoly of traditional database companies like Oracle or databases or relational databases was broken, and whole of big data started, right, in the early 2000s because of internet companies, especially Google. So one other thing we should know is no single tool can achieve everything. That's very, very important. This is one thing that many people get confused, whether it is Hadoop or whether it is a standard database like MySQL, or whether it is Spark, right? Or whether it's a NoSQL database like MongoDB. Each of these have their specific roles. For example, at Applied AI course, we use MySQL to store all of our customer or student data, right? Because we don't need Hadoop. The scale at which we are operating today, we don't need Hadoop. We are sitting on probably a few gigabytes of data or few hundreds of GB of data. That's all. We are not even a terabyte scale. So I don't have to go to Hadoop or Spark or MongoDB or any special things for this. Of course, at Applied AI course, we have some applications of NoSQL databases also. I'll come to that at the end of this session or in the later parts of this session. But for our needs, MySQL will do the job. It is very cheap to maintain. It is very easy to build. While if I were when I was working at Amazon or even at Yahoo Labs, right, back in 2009, I joined Yahoo Labs back in 2009, right? So Hadoop was the only way we could literally process data, because we were sitting on hundreds of terabytes of data or even petabytes of data. And of course, slowly from around 2014 onwards, Spark became popular. Again, we'll understand why Spark became popular a little later. Then we moved into the world of NoSQL databases, everything. So just like in machine learning, no single model can be good for all problems. Even here, no single tool or no single database or big data tool can achieve everything. Every tool has its purpose and place. Okay, so don't try to force fit and say, oh, I'll use Hadoop for this problem without even having the need for Hadoop. Again, we'll understand what is the need for Hadoop and all of that little later, right? So very key thing that you have to remember is no single tool can achieve everything. Every task needs its own set of tools. Every tool has its advantages and disadvantages. That's very, very important. So now, since we're talking about data, let's take a slightly different angle to it. Let's move to a slightly different angle called parallel processing. So what happened was, if you think about it, so a very interesting thing that happened was, so before 2000s, okay, so before your 2000s, there were supercomputers, obviously. There were supercomputers, right? But what were the supercomputers mostly doing? Supercomputers were used for weather forecasting. Supercomputers were used for weather forecasting. They were used for military purposes, for nuclear experiments, okay, for scientific research, right? For scientific research. And of course, for drug discovery and all of these things. But all these tasks are called compute-heavy tasks. All these tasks are called compute-heavy tasks. So there are two types of tasks typically, compute heavy and data heavy. It is important to understand the difference between both, right? Suppose, I'll give you an example. If you've gone through some parts of the course, you'll be able to understand it better. So your big data systems, okay, so your big data systems, unlike your supercomputers, right, are good at data heavy tasks, while supercomputers are good at compute heavy tasks. What is a compute heavy task? Imagine if you have to build a system for weather forecasting or for nuclear research or for any scientific research for that matter. The amount of computations that you have to do, the amount of, weather forecasting is basically a bunch of differential equations. Is basically a lot of differential equations. Okay, lots of differential equations that you have to solve. And there is lot of algorithms like your gradient descent and stochastic gradient descent. Algorithms like them. I'm not saying exactly SGD and GD, but optimization algorithms are compute heavy in general, because optimization algorithms repeatedly or iteratively perform a lot of updates, right? So all these tasks typically were compute heavy in the sense that they might not work on large amounts of data. They might work on only on a few terabytes of data, but still they needed supercomputing power because the amount of computation that they had to do. Imagine deep learning. Imagine performing deep learning on small data, on small amounts of data, let's say, right? On small amounts of data. If you're performing deep learning, remember deep learning is compute heavy because there are millions of weights that you have to update in each iteration of your stochastic gradient descent or variations of SGD. There is a lot of computation that you have to perform, even especially if you're doing deep learning on small amounts of data, right? So those tasks were very well done on standard supercomputers built by companies like IBM at that time. This is before 2000s. But what happened after 2000s was we are no more, of course, all these applications still remain. All these applications still remain. They're still supercomputers today, right? But we moved into a data heavy world. Of course, compute heavy was there for all these tasks, but a new type of task called data heavy stuff. For example, if I'm crawling the internet, right? If I'm crawling the internet, I'm literally sitting on petabytes of data, even in early 2000s, right? I'm sitting on literally petabytes of data, and typical supercomputers were not designed to handle this large amounts of data. They were designed to parallel process. They were designed to parallelly process. They were designed to parallel process tons of data. And this parallel processing came because see, you have your CPU, right? This is your CPU. So your CPU typically has four, if you have a 4-core box, what does it mean? It basically has 4 compute cores, which means 4 tasks can be run parallelly. So supercomputers in those days had basically tens or even close to almost 100 core. Okay, they were almost close to like tens of cores available in a supercomputer, because then it can do hundreds of or even thousands in some cases of parallel jobs, right? So they were called parallel processing systems in those days. Supercomputers were parallel processing systems. And some of you computer science students would have studied parallel computing in your courses, okay, in which you would study about supercomputers and not about big data systems. Unfortunately, our course curriculum hasn't evolved to meet the needs of the industry, right? So on the other hand, companies like Google, Amazon, they were sitting on petabytes of data literally. And this is data heavy. It's not compute heavy because we are not doing a lot of optimization, unless because deep learning did not come into the scene till about 2012, right? So between 2000, in the early 2000s, even up to early 2010s, we are sitting on a lot of data, and we just had to do simple operations on data, like the way we have seen in SQL, joining the data, grouping the data, counts. These were simple operations that I had to perform on this data. This is not compute heavy, but this is data heavy because I'm literally sitting on hundreds or even thousands of terabytes of data. So the earlier supercomputers versus the current big data systems, there is a difference. And both these systems merge with deep learning on large data sets. Today, when we do deep learning on large data sets, right? Deep learning on large data sets is both data heavy. It is both data heavy and compute heavy, right? Because imagine building a image classifier on ImageNet data. There is tons of data. There are millions of images out there. And it's also compute heavy because deep learning itself is a very compute heavy task, because you're updating millions of weights, especially if you're taking a state-of-the-art deep learning model, right? Even things like AlexNet that we've discussed in the deep learning sections of our course, it's super compute heavy, right? So deep learning on large data sets is both. It's both compute heavy and data heavy. So this is the third application which has become more popular, I think, from 2015 onwards, right? Supercomputers have been there from 1970s, almost 1980s also. The big data systems came only in the early 2000s, just to give you some historical perspective here, right? So in the old world, when we had parallel processing systems like supercomputing systems, there were two popular platforms or two popular libraries that were very popular. One is called Mpi, the other is called Pbm. Okay, so those of you who have studied parallel processing might have encountered these terms called Mpi and Pbm. So they were basically simple libraries. You can think of them as libraries or frameworks to be able to leverage these supercomputers with hundreds of cores. You could have hundreds of cores of data or even tens of cores. So they were designed for supercomputer applications, and also something called as grid processing. We don't use the word grid computing anymore because of cloud computing. But anyway, so pre-2004, parallel processing using Mpi and Pbm were very popular. So if you're reading some libraries, some code libraries from the 90s or even early 2000s, you might encounter these words. Okay, these are basically parallel processing libraries before big data, and these are useful for compute heavy tasks. These are very good for compute heavy tasks. Actually, lot of code design ideas in TensorFlow were actually borrowed from MPI and Pbm. Okay, MPI is more advanced than Pbm. I think Pbm was there in the 1970s and MPI in the 1980s and 90s, right? So, but both of these were meant for compute heavy tasks. We don't use them as much anymore today. Okay, so now let's go into the data part of it, right? So if you look at the, again, I've provided some Wikipedia links here. Wikipedia is probably the best and the most trustworthy. So now let's move on to traditional databases, right? So this is from 1970s onwards, right? We had Oracle, which became a giant corporation. We had MySQL, which is a very popular open source database. PostgreSQL, which is a very popular open source database from University of California, Berkeley. By the way, University of California, Berkeley is one of the pioneers in many of the database architectures. Even Spark was built at University of California at Berkeley. So UCB, or Berkeley as it is often referred to as, is one of probably the best universities in the world for computer science, and especially for systems. So a lot of operating system concepts were designed at Berkeley, a lot of distributed system concepts, right? So it's one of the best places probably in the world for operating systems, distributed systems, even databases, right? While we hear about Stanford a lot for machine learning, Berkeley is certainly the best place. And these two universities are not very far away. They're like what? They're like 100 kilometers away from each other, right? So Berkeley is brilliant place for operating systems, distributed systems, and databases in general. So what happened was, so Berkeley, the University of California, Berkeley literally built an open source PostgreSQL. IBM had this phenomenal tool called DB2. Microsoft has SQL Server, right? So all these were traditional relational databases. All these were traditional relational databases which were storing data in tables, as we have seen in our SQL chapters. What is the core idea behind all of them? Okay, remember, in the 1970s, this is a very important historical and technological perspective we need to have. In the 1970s, almost up to 2000s, early 2000s, almost up to early 2000s, hard disks were not cheap. Storage on disk was not cheap. It was fairly expensive. It was not at all cheap, right? So what many of these relational databases, so there is this whole area called as relational algebra. There is this whole area in computer science called relational algebra, which is the mathematics behind relational databases, which Boy and Cord designed in the 1970s. Now, the biggest technological constraint they were working under was that hard disks were not cheap. Hard disks were expensive in those days, right? Because hard disks were expensive, people wanted to minimize the amount of data they were storing. So people said, I want to store all of my data as efficiently as possible. So they were okay to wait a few hours. So your wait time was not a major concern. People were willing to wait a few minutes or even a few hours to get their query results. Okay, so suppose if I ask a query to a relational database, I'm willing to wait for a few minutes or even in some cases a few hours to get my result. But since hard disks were expensive, I wanted to minimize the amount of disk space I was consuming to store the data. That's why you have this whole concept called as normalization, right? So the whole concept of normalization that we've discussed in the course videos in SQL chapter, the whole concept of normalization says, I want to minimize duplicate storage of data. I want to minimize duplicate storage of data. I want to minimize this data. Basically, I don't want any duplicates to be stored as much as I can. That's the core idea behind whole of database normalization, right? And all of your relational databases were designed around normalization of data. So they were trying to minimize duplicates, thereby minimizing the amount of space required on hard disks. This was the reality almost till early 2000s. But things change in early 2000s. The cost of hard disks comes super fast down. Again, I'll show you a plot which shows how the cost of hard disks have come down dramatically since the early 2000s. Now, the moment the cost of hard disk or disk itself comes down, I don't have to worry about minimizing. See, the moment, so imagine if storing 1 terabyte of data was costing me $1,000 earlier, if it is costing me like $100 now, right? Then I did not worry about minimization of data. Today in the internet world, people don't want to wait. Google did not want you to wait for even a few minutes for their search results to be available. Google told you that I'll give you search results in split seconds. So wait times became more important. I don't want to wait. In other words, I want to have low latency applications. I don't want to wait because my disks have become cheaper, right? This is a big change that has happened. This is a sea change in computer science that has happened in the early 2000s. Your hard disks became extremely cheap and people became less patient. And of course, thanks to the internet companies, they made us less patient, okay? Because they innovated on this space. So today, if I have to imagine a world where I Google search and I have to wait for minutes to get a result, Google will simply die. People will stop using Google, right? But that was not the world till almost late 90s and early 2000s, right? Most traditional databases, there would be wait time. Even today, I've seen databases being used at Amazon, Oracle databases and data warehouses, where I had to wait a few minutes or even tens of minutes in some instances to get results to my queries. Imagine, I would never do that if I'm searching on Amazon or if I'm searching on Google or Facebook, right? So this is the sea change. The hard disk became cheaper and people became less patient, or people did not want to wait. And we'll see how some of these problems got resolved. Other thing was, most of these traditional relational databases were hosted on a single box, or it's also called as a database server. All these were hosted in a single box called a database server, which was a very powerful computer, certainly a powerful computer with a lot of storage, but nonetheless, it was mostly a single box with multi-core, right? So this was the world of databases and data storage till late 90s and even early 2000s. This was the world in which Google comes and innovates. Okay, so we'll take a little break before we'll take a 5-minute break. I'll just take a quick sip of water, and then we'll go into, because now we have a historical context on what happened before, what worked, what did not work, right? So we will be much better. Just a second. Okay, so since we have the historical perspective, we will be able to much better appreciate Mapreduce, Spark, and all of these things. So I'll start from 2004 onwards, from the time Google came out with Mapreduce and the design behind Hadoop and things like that. Okay, we have a lot of turf to cover. Let's try and cover as much as possible, but I'll try to avoid rushing, because then nobody wins here, right? We can always have multiple sessions on these topics. So today I'm going to give you an overview to get a sense of what is happening, what is what, why do we have some of these things, what are the historical technological changes that led us to this. And then, of course, if we cannot finish this, we can always have a second session or a third session on this. So let's go slowly, but let's get the concepts clear. In the meantime, I'll also just look at, let's also look at these, what volume of data can be considered big data. That changes every year. 10 years back, 10 terabytes or 100 terabytes was considered big data. Today, that's considered a joke. Today, at least a few petabyte is considered a big data problem. So things change a lot. Okay, and again, what should I learn, DBMS or big data? You should learn the basics of DBMS first if you want to learn anything, because that's like foundational stuff. If you don't know SQL, if you don't know basics of databases, learning big data is like trying to write poetry without knowing alphabets and grammar. Okay, so let me answer while I'm sipping some water. Let me answer these. So somebody was asking about previous live videos. The live sessions that we've done on YouTube are on YouTube. The live sessions that we have done limited to our students are on the desktop app, right? So please check that. Somebody was asking about the Google Doc for the last session. At the end of session, within 1 hour of completion of the session, I would share all of these docs. So please make a note of them, right? So I always share, like last session, I think I shared within 10 minutes of the completion of the session. So I'll also share today. Please make a note of it. And okay. What large data, how large data, big data, I mean, the data size changes every year, as I told you earlier, right? So, okay. So if you want to learn databases, my first suggestion, somebody is asking about databases. So the first thing you should start is, in the course, we give you a basic introduction to databases with things like what is SQL, why do we need normalization. Please first start there. But if you want to really learn deeply, we would have some course on databases in the next 3 to 4 months, because now we have started doing all the foundational courses of computer science, right? So probably 3 months down the line, you could have a database course from us itself, because we felt a lot of students do not have foundational computer science knowledge, even computer science graduates. So we're doing a lot of these foundational computer science courses like data structures, algorithms, basics of C programming, databases, operating systems, etc. Right? So you'd probably have a DBMS course from us in the next 3 months. But in the meantime, please go through the SQL and other stuff in our course. If you want to pick a book, there is this very nice book by Professor Raguramakrishnan. Very seminal book, very popular book. Please pick it up. Certainly help you. Okay, some of these people who are asking me about applications in some specific area, it's actually a Google search away. So you could just say deep learning applications in space, right? I'm sure somebody, because I'm not an expert in space exploration or anything, my answers would only be shallow, to be honest. Okay, so it's best if you just Google search for it, and the answers are just sitting around there, right? Oh, so yeah. Somebody was asking about Oracle DBs allowing us to tune queries below 10 milliseconds, and companies are normally ready to add cores. Yeah. So Oracle is also caught up, by the way. Oracle was a laggard. Oracle did not innovate while big data technologies were picking up. Today, by the way, large companies like Amazon are moving out of Oracle databases because of big data technologies and cloud platforms. So Oracle, of course, had to innovate. So that's why I said databases of Oracle in the 70s, 80s, and 90s. Oracle certainly caught up. If Oracle did not caught up, it would have become a dinosaur. It has caught up. It has also done some interesting stuff of their own. But if you work at a major technology company, Oracle is still seen as a dinosaur because they're not innovating as fast as people want. And today, cloud databases are a big threat to Oracle. See, even today, Oracle is still surviving because of their legacy systems. There are hundreds of non-technology companies. Like think of non-tech companies, right? Like your insurance companies, your flight reservation companies, your flight company, your airplane companies. All of them still use databases. It's only the tech giants who can afford to innovate, who have phenomenal software engineers, who are moving away from Oracle. Like I think Amazon announced that they've moved all of their retail stack away from Oracle, and they're using their own cloud infrastructure today, right? So I think Oracle is a phenomenal company in the sense that they do phenomenal sales, but I don't see them as a pioneer in technology. I think it's probably Google which is the best pioneer in terms of I won't even call Amazon. Probably Google is the best pioneer in terms of data technologies, right? Okay. Okay, somebody's asking about performance tuning on Hadoop. We didn't even cover what Hadoop is. Performance tuning is a big task in Hadoop. Let's be honest about it. You need to do a lot of tests. So that's a very deep topic that I'll not be able to cover here. Sorry. Okay, sounds good. Yeah, I'll try to cover about Spark a little. Yeah, of course, I'll mention about PySpark. PySpark is nothing but getting all the functionality of Spark in Python. That's it, right? Because anyway, we'll go to that. Okay, sounds good. Okay, let's go here. Okay, so back to the discussion. So now what the big changes that have happened are okay, let me change the colors here. Okay, let's move to red. So what Google did from almost late 98 to 2004 is Google started solving its own problems. Jeff Dean and even the co-founders of Google, right? They had a terrific co-founding team. And most of the initial engineers at Google were from Stanford, terrific software engineers, phenomenal engineers nonetheless. So they built their own internal system, right? They built their own internal system. They said Oracle's databases in those days were not scaling to their needs. They said, let's build our own system, which would satisfy all the constraints that they wanted. That it had to be cheap, it had to be scalable as internet grew, right? And it has to be very cost effective or cheap, basically. The cost has to be low. And it has to be it has to solve their problem. They said, I don't want to build a general purpose database. I want to solve my own problem. That's what their concern is. So Google said, here is my problem where I'm sitting on petabytes of data. I want to process this data as fast as possible, and I want to make this searchable fast. That's their task. Their task is not to build a general purpose database like what Oracle builds or anybody builds, right? So Google worked on a system called as Mapreduce. Okay, Google published this seminal paper in 2004. One of the authors of this is Jeff Dean. So this is actually the research paper that they published in 2004. Okay, Jeff Dean, and there is an Indian author also. I forgot his name. He's a second author, but it's a terrific system that they've designed. So Mapreduce, in a nutshell, what Mapreduce does is very interesting. It says, okay, so we'll come to what Mapreduce does in a while, right? And Hadoop, which is a project which started around 2006, 2007, is what the Hadoop project. Hadoop is an open source project. What Hadoop did was it took this research paper that Google published in 2004, and they started implementing it in an open source platform. That's what Hadoop is. Hadoop is basically the most popular implementation of Mapreduce. There is also some controversy around Mapreduce itself, because Mapreduce is not something that Google invented. Google did not invent Mapreduce, even though they have a patent for it, and there is a lot of criticism against that. Google did not invent Mapreduce. Mapreduce as a paradigm of distributed computing was invented at Berkeley. By people like Stonebreaker, so who's again a phenomenal scientist at Berkeley, right? On databases and things like that. Stonebreaker is like he did a ton of companies. I think he now teaches at MIT, if I'm not wrong. So they actually came up with some of the core ideas of Mapreduce almost 10-15 years earlier to Google. But what Google did was Google borrowed these concepts from research and they implemented it phenomenally well. So Google here did not do the fundamental research, but Google did the engineering so well. Google was an engineering genius here. They took all of the research that existed and they put all of them together in an engineering system called Mapreduce that Google built internally and used extensively, right? So the core tenets of this are these, right? So Google said, I have these simple desktops. At my disposal. They're cheap, right? If you just take instead of taking the whole desktop, if you just take the motherboard, if you just take the motherboard, right? The motherboard has all the components, right? On the motherboard, I have my CPU, I have my RAM. I can also connect a hard disk to it, right? I can power it up. All of the key components that I have are there on a motherboard. Some motherboards also have the cooling fan, right? If you've ever opened a laptop or a desktop, you'll see a motherboard inside, right? So Google said that these consumer level motherboards, okay, are cheap. These are consumer level. These are not special purpose. These are stuff that you can go to any market and buy, right? You can go to any electronic store in the US or even in India, and you can buy these motherboards. They're very cheap, right? So they realized that these motherboards were cheap hardware because they wanted cost-effective solutions. So they started using these motherboards which were readily available, number one. And they realized that the cost of disk was coming down. So they said, okay, data storage should not be a problem because the cost of disk was coming down by the time Google was designing these systems. And they also had fast LANs, right? You started to see 100 Mbps LANs around the same time. So what I could do is, so I'll show you an image. I think it's on the internet for sure. So because I saw that Google first cluster. You can get this image. Yes. Okay. So I saw this in the Computer Science Museum in Mountain View. So this is the first system that Google built. This is called a cluster. So if you notice, what Google has built here is basically each of these is a motherboard. This 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 is a motherboard, etc. This is right now there in the Computer Science Museum in Mountain View, right next to Google Office, right? So you have each of these is a motherboard. So what they've done is they've taken lots of motherboards. They've connected all of them through your Ethernet cables. All these are Ethernet cables, right? So they've literally connected, I think about 20 or 30 motherboards here, right? In a single box. Of course, this needs to be cooled. Otherwise, this whole thing will melt away, right? So they literally took these motherboards. Each of these motherboards has all the components. Each of these motherboards would have a CPU, would have RAM. It would also have a hard disk drive. It would have all the components, right? And it would also, they were also using this LAN to connect all of them. So they said, we have a lot of data and each of these motherboards could have a hard disk. So what if the total data that I have, right? So they said, what if the total data that I have, imagine this is one box, imagine this is the second box, imagine each of them, so on and so forth. I have lots of these motherboards. Each motherboard has a CPU, has a RAM, and has a hard disk drive, and of course has some network connectivity. So all these are connected via your LAN. Okay, all these are interconnected through your LAN, right? And now it said, if I have large amounts of data, why don't I break this data? Why don't I break this large amount of data and store each chunk of this data in one? So this chunk, I could store it in this hard disk. This chunk, I can store it in the other hard disk. This chunk, I can store it in the third hard disk, and so on and so forth. So they were basically distributing data. So they were basically distributing data across multiple hard disks. And they said, because I have these fast LANs, these LANs were like 100 Mbps LANs in those days. We still did not have Gbps, 1 Gbps or 10 Gbps LANs then, if I'm not wrong. Again, I'm not an expert in networking, so just correct me if I mentioned something wrong here. But I think in the early 2000s, 100 Mbps was the best speed. So because I had 100 Mbps, I can copy data from this hard disk to this hard disk very fast if I want, through the LAN, right? Through the Ethernet cable. Right? This was, and remember, each of these is very cheap. Each of this is very cheap. Each of this was cheap. Suppose, imagine if I have, let's say, some 50 motherboards stacked up like this. Tomorrow, if I want to increase my capacity, I can add 50 more motherboards, right? So it is extremely scalable. It is extremely scalable because I can add 50 more. I can just add more connections and everything will work. So it was extremely scalable. It was extremely cheap, because I was basically taking off-the-shelf motherboards. I'm not doing any advanced motherboards here. Simple motherboard that I was getting, that I was buying for my regular laptops and desktops, I was using them, right? So literally, Google built a system like this from scratch. And they wrote a layer called Mapreduce on top of it. And all of these were running Linux, by the way. All of these systems were running Linux. And on top of Linux, Google wrote something called as Mapreduce. What Mapreduce effectively did, so Mapreduce basically has two tasks. Broadly speaking, it has two tasks. It has one thing called as Hdfs. So that's for Hadoop, basically. Okay, so let's not write Hdfs right now. So it has two things. It has a file system, and it has a compute. It has a compute coordination system. Two parts. What is a file system? A file system basically says, given a large file or large amount of data, how do I split this data across multiple hard disks? Your typical file system, if you think about a typical file system in your laptop or desktop, what does a file system do? A file system manages all of the data that you have on your disk, on your hard disk or solid state drive, etc. Right here, they had to write a new form of file system because this was a distributed file system that was distributing parts of data on various things. And whenever I need some data here, which is not present here, I need to pull this data via the LAN, via the Ethernet cable, right? So they wrote very impressive piece of software where, suppose if on this box, I needed some data that is there in this hard disk. So it would just flow through these LAN cables and come here, right? So they wrote all of that orchestration software, which is basically the distributed system files, the distributed file system they've written. And they also wrote the compute, which is given a task. Suppose I have two large tables like this. Extremely large tables, and I want to join both of them. I mean, in databases, like we have seen in SQL, right? You have to join two large tables. Let's assume this is 100 terabyte table, and this is 1 petabyte table. If I want to join both of them on some key, let's say I want to join both of them on some key, how do I join them? Right? There is a lot of data transfer that has to happen over the Ethernet cable. There is a lot of processing that needs to be distributed. So what Google literally wrote is basically the whole compute layer on top of it. So Mapreduce consists of two parts. How do you orchestrate the computation, and how do you store the data? Okay, we will not go into the depths of Hadoop on how the file system works, how the compute infrastructure works, and all of that. But that's what Google wrote literally. Okay, and they published all of their research in 2004 on how they've built the system. Immediately, there is a lot of interest because there are so many other internet companies struggling with the same problem. Yahoo, which today is no more a large internet company, was a giant company at that time. Yahoo immediately took notice. Yahoo realized that, yes, this is the same problem that we are running into. Yahoo had a search engine of their own, and Yahoo was the most visited web property at that time, before Google took over Yahoo, or took over took over the first position from Yahoo, right? So Google said, we will use cheap hardware, we will use fast LANs, we will use the hard disk price that is coming down. We would do all of that and come up with something called as Mapreduce Architecture. So Hadoop is an open source project that a bunch of very brilliant software engineers started after reading the Google research paper. And one of the biggest funders of Hadoop was Yahoo in those days, because Yahoo said, I need this system. Let these open source developers build it for me, right? So again, there is this very nice slide here that I wanted to show you. So this is basically, this shows the price of, okay, so this shows the price of, let me just zoom this in a little. So this is the price of hard disk, the cost per gigabyte, So this is the cost per gigabyte of storage from 1980 up to 2010. Notice that this is log scale. This is not linear scale. So this is 10 times this. This is 10 times this. So in 1980, the cost of 1 GB of space, or of 1 GB of hard disk, was above 100,000, was almost close to $200,000. $200,000. Okay. Today, it is closer to, I think it's today closer to 1 cent in 2019. This is only till 2010. Even in 2010, it was like some 8 cents. Look at the difference that we have come in 30 years, the cost of hard disks. You'll notice that from 2000 onwards, the costs have also fallen very sharply. There's so many new hard disks that came into existence, right? So the cost of hard disk has fallen so dramatically in the last 20 years that storing data became the trivial thing now, right? So the cost of storage has plummeted. There's also more articles that I've linked here. Okay, there's also an article that I've linked here. Just go through that. Now, we have talked about what is data intensive and compute intensive tasks. Most of the tasks that Google was doing were data intensive, not compute intensive. So Hadoop is very good for data intensive tasks. Imagine if I have to process a petabyte of data. Imagine if I have to join two tables where one table was 1 petabyte, the other table was 100 terabyte. This is data intensive. This is basically a simple join operation. This is not like building a machine learning model. See, compute intense tasks are mostly iterative tasks, like your stochastic gradient descent and things like that. Or optimization algorithms in general are compute intensive. Google was not trying to do a compute intensive task. Google was trying to do data intensive tasks because it literally crawled the whole internet. So it designed Mapreduce to be very good for data intensive tasks, not for compute intensive tasks, right? So, and the file system that Hadoop designed using Google's published research paper is called Hdfs, which stands for Hadoop Distributed File System. Okay, so this is the file system which literally breaks up your data, stores it into smaller pieces, and ensures that everything is working, right? Just give me a quick 5 seconds. Okay, so where were we? So Hdfs is the file system on Hadoop. It's a distributed file system to ensure that if you don't have data, the data will be pulled through LAN, all of this stuff, all of the orchestration of storing the data across multiple hard disks is done by Hdfs, right? Then comes a very interesting thing. People said, we're sitting on all of this data. Many of our people know SQL, because SQL has been there from almost early 90s, if I'm not wrong, or maybe even in 80s there was SQL. Okay, I think the SQL standard came into existence in 92, if I'm not wrong. Okay, so a lot of people knew SQL. So why don't we have, so we have this whole data, right? We have all of this data sitting in your hard disks. What if I could write what I want in SQL, right? So because the interface to query this whole thing, because I may not be an expert in distributed systems. Imagine I may not be an expert in distributed systems and Hadoop, but if I know SQL, which many programmers knew at that time, many programmers did not know about Hadoop and distributed computing, all of that. But many programmers knew SQL because they were using classical traditional databases. So companies like Yahoo Research and Facebook, they said, we have a lot of people who know SQL who do not want to be worried about the distributed system, because learning distributed systems, becoming an expert at it, writing good distributed system software is very time taking. So what this company said is, what if I write my code in SQL, right? What if I write my code in SQL? There is some engine sitting in between, which will convert them into MapReduce tasks, which will convert them into MapReduce code, right? This every most software engineers knew SQL. So they said, if somebody could write SQL query, imagine I have an engine in between, which converted these SQL queries to MapReduce, and this I can execute on my Hadoop cluster. My MapReduce programs I can execute on my Hadoop, right? What if that's possible? So two major research projects that started were called Pig and Hive. Pig was started by Yahoo Research, and I joined Yahoo Research in 2009 in Bangalore. So when I joined Yahoo Research, Pig was one of the most popular tools that a lot of engineers and scientists at Yahoo Labs and Yahoo Research were using extensively to use Hadoop. And I was one of the early people who have been very lucky to actually use Hadoop in production environment. So my team in 2009 was using Hadoop in production on actual real world machine learning tasks, right? Of course, I'll tell you what are the problems that Hadoop had at that time also in a little while. But we got lucky, and I got very lucky. Straight out of college, I joined Yahoo Labs, and I got very lucky. I learned Pig in 2009. Very early stages of Pig. It was still not a production quality. It was still there, and I learned a lot about how Pig was designed. And so this became, so some companies used Pig, some companies used Hive, right? So I started using Pig from around 2009. So in Pig, basically what you write is the code. Okay, I'll show you some examples here in a little while. If you want to learn Pig, Pig is very much like SQL. If you know SQL, you can learn Pig over a weekend. Okay, just the way Yahoo Research was building Pig, there is another tool called Hive that Facebook built. So Hive was closer to SQL than Pig. I'll show you some examples in a little while. Hive was much closer to SQL than Pig. So Hive has something called as HiveQL. So Pig, of course, was getting popularity, but Facebook said, no, we don't want our engineers, analysts to learn. So because Pig was slightly different from a traditional SQL. So Facebook started building something called as Hive, where they had something called as a Hive query language, or HQL or HiveQL, which is very, very similar to SQL, right? And if you want to learn Hive also, it's straightforward. It's straightforward because it's very similar to SQL, right? So I'll show you some simple code in, so let me show you some simple code in Pig and Hive, right? Just to give you a sense of how easy it is. Okay, see, look at this. So Pig is also called as Pig Latin. So the code that you write in Pig language is called Pig Latin. If you notice, you're loading data here, you're applying a filter operation here. Remember in SQL, we learned filter operation. Now you're joining two tables. You're grouping them, you're grouping some data, right? There is something called as a for each, then there is filter, then there is order. Dump basically means store. This is how Pig Latin looks. So there is a very nice mapping from each of the commands in Pig Latin to what you do in SQL. While HiveQL, if you look at this is how HiveQL looks like. HiveQL looks very much like your standard SQL, right? Pig Latin is slightly different from HiveQL, but both of them are popular, right? So if you know Hive, so I see a lot of people. So I used to interview senior engineers and managers at Amazon. So some people used to say, I know Hive. I used to ask them, what do you know in Hive? So they would say, I know Hive. Okay, I say, okay, how does Hive perform join operation internally? They don't know. So what they know is basically HiveQL. So a lot of people who claim that they know Hive, they actually know HiveQL, which is nothing but SQL only. They don't know how Hive works internally. Because if you know SQL, HiveQL is like 5 hours you can pick up HiveQL. 90% of the syntax is the same. Pig, of course, Pig might take you a couple of days to pick it up because Pig syntax is slightly different, right? So when people claim that they know Pig or Hive, many people, what they mean is they know how to write this code. They don't know what is happening internally, right? They don't know how Hadoop, how Pig works internally. But if you're looking for a top-notch company as a software engineer, especially, you need to know that. Okay. Okay, sounds good. Where was I? Notes. Okay, so yeah, here we are. So Hive was built at Facebook. Pig was built at Yahoo Research. So all of that was good. Good. So RAM available over time. Okay, so all this was good. But still, Pig was, so all of Hadoop, if you think about it, Hadoop was good for data intensive tasks, not for compute intensive tasks. So this was a problem that I was facing in around 2009 at Yahoo Labs, right? So we were sitting on a few hundred terabytes of data. We were building models for search advertising for Yahoo. In those days, Yahoo had their own search engine, and Yahoo was also doing their own search ads. So my team was responsible for search ads in Southeast Asia, in whole of South Asia, actually. So we're sitting on this data. We had to build a logistic regression model, right? We had to build a simple logistic regression model. Now, logistic regression model, of course, we have large amounts of data. Logistic regression also has some compute because you're constantly updating your weight vector, right? Through SGD, right? So what happened then was we realized that while it is very good to process 100 TB of data using Hadoop, Hadoop was very bad to do distributed machine learning. Why? Because it was not good for compute intensive tasks. It was not good for iterative tasks. It was not at all good for iterative tasks. Not at all good. Even for simple logistic regression, it used to take us a lot of time. So it was terrible for iterative tasks because iterative tasks are compute intensive because you have to constantly compute new weight vectors all the time, right? So that was the biggest problem with Hadoop. So there was a project called as Mahute. Which tried to build a machine learning library on Hadoop. This was a catastrophic failure. It never worked. So my team, we had to build our own system to build logistic regression, to train a logistic regression model on Hadoop from scratch ourselves, because we didn't have toolkits in those days. So my team literally built it from scratch. One of the things that Hadoop does is Hadoop stores all intermediate data. So while doing this whole thing, right? When Hadoop was designed, right? Suppose I'm doing some join. I would have some intermediate data in the code. All the intermediate data was being stored into hard disks. So one of the things that was happening was Hadoop stores all intermediate data to disk. Because when Hadoop was designed, we did not have enough RAM. We did not have enough RAM in our boxes around 2006, 2007. Right? Since we did not have enough RAM, you could not store the intermediate data because the intermediate data was also a few GB. In many instances, even the intermediate data was a few gigabytes. This intermediate data could not be stored in RAM because your RAMs were still like 1 GB or even 2 GB of RAM. You did not have the world where you have 32 GB or 64 GB or even 128 GB of RAM, which is very common today. We did not have this in 2006, 2007. So when Hadoop was designed, because they did not have enough RAM in the boxes, and Hadoop was built on simple consumer grade boxes, right, which had 1 or 2 GB of RAM typically. So all the intermediate data was stored to disk. And remember that in computer science, this is a very, 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 very important thing in computer science. Storing anything, suppose let's assume this is your CPU, let's assume this is your RAM, and this is your disk, right? Reading any data. So typically what happens is CPU can read data from RAM very fast. But for CPU to read data from disk via the RAM is very, very time taking, extremely time taking. That's why when you're loading large files on your computer, when you're reading it from your hard disk, it takes a lot of time, right? So while if the data is stored in the RAM, you can read it very fast. Because all the intermediate data was being stored to disk, loading this data back in and doing some compute on top of it was very expensive. And of course, Hadoop was the right choice because in those days, there was not enough RAM. So they said, if I don't have enough RAM, what do? I store all intermediate data to disk, right? So that's what happened till the time Spark came across. So again, now there's a huge change again in the world of technology. Just like the way hard disk spaces came down, hard disk costs came down, and the size of hard disks increased, which made us go from traditional databases to Hadoop. Same thing again happened within a few years. This time it happened with RAM. Okay, look at this. There is this very nice thread on Reddit, which I saw. So in 82 to 84, 1 KB to 64 KB of RAM is considered big deal. Okay. Even till 2009 or even till 2010, 3 to 4 GB was considered big deal. Today, 32 GB and 48 GB are considered norm. I have a smartphone with 8 GB of RAM. Right? Just imagine I have a smartphone with 8 GB of RAM. That's a massive amount of RAM, right? So today, the cost of RAM has come down and the amount of RAM has increased dramatically in the last 10 years. So that's the world into which Spark is born, right? So Spark comes into existence because RAM became cheaper. The size of RAM has grown and the cost of RAM also has has reduced. So the big question that researchers at Berkeley asked was, the biggest problem with Hadoop was all the intermediate data was being stored to disk, which was making the whole thing slow. And hence I can't use it for compute intense tasks. Right? I'm not able to do compute intense tasks because all the intermediate data is being stored to disk. That's because I don't have RAM. But the world immediately changed by around 2012 to 2014. I think the Spark project started in 2012. Version 1 was launched in 2014 or 2013, sometime around this time. Because my team at Amazon started using Spark from the very early days, because we noticed the power of Spark very early. And I think we were one of the earliest teams to use Spark for machine learning use cases. So the RAM sizes have grown massively. So the researchers at Berkeley said, why don't we use this RAM more effectively? Why should we stick to Hadoop? So they literally redid whole of Hadoop, right? They had all the advantages that Hadoop has, the MapReduce paradigm. So you can think of Spark as a superset of Hadoop, where it said, if the intermediate data can be stored into my RAM, let it be in my RAM. If it doesn't fit into my RAM, then I'll store it into disk. This was one of the big differences between Spark and Hadoop from a design perspective. Of course, Spark was written in a language called as Scala, right, which very few programmers knew, right, including I also didn't know. I learned Scala only to write initial Spark code. I didn't know about Scala. But the developers of Spark soon realized that many programmers don't know Scala. So they launched something called as PySpark, which they said, okay, there are a lot of developers who know Python, and they also have Java version of Spark now. Okay. Again, there is a lot of relationship between Java and Scala and things like that. So they said, if you know Java or Python, you can start writing Spark code. And lot of developers knew Python and Java. They didn't know Scala. Of course, some programmers did learn Scala, but many of them said, okay, I'll just continue to use Python and Java. Lazy programmers like me, people who didn't want to learn or relearn everything, we said, okay, thank goodness I don't have to become a Scala expert. I moved to PySpark as soon as it was announced and launched, even in the beta version. Okay, so around 2012 to 2014, right? Version 1, I think it started in 2012 and the first version was launched in 2014. Spark was launched. And Spark was using the larger RAMs and the cheaper RAMs more effectively than Hadoop. So the moment you're using RAM more effectively, you can do iterative tasks better. Because iterative tasks work better if all of your data can be stored in RAM. Because disk read is much slower, but reading from RAM is very fast to the CPU, right? So iterative tasks, because the data is stored in RAM, iterative tasks are faster. The moment iterative tasks are faster, I can do compute intensive tasks. Right? What type of compute intense tasks? Machine learning is a very good application of compute intensive tasks, right? So what Spark gave me is, Spark could process large amounts of data. For me because it was using Hdfs in the background. It was using RAM if data could fit in RAM. If data didn't fit into RAM, it would store into disk. So it had all the advantages of Hadoop. It could handle large amounts of data. It could also do iterative and compute intense tasks effectively for me, thereby becoming one of the best tools for whole of machine learning. So Spark MLlib, we have discussed Spark MLlib in one of our live sessions, right, called productionization of machine learning models, right? Again, Spark MLlib is very easy to pick it up. If you know basically what you have is, you have a slightly different library with different functions. And Spark MLlib, you can write code in Python also. Right? So all the documentation I've placed here. And the good thing is, Hive and Pig now modified their source codes to work on Spark also, not just on Hadoop. And Spark itself had something called as Spark SQL. So literally, Spark replaced Hadoop in many companies, primarily because Spark had all the advantages of Hadoop, along with the advantage that you could do iterative and compute intense tasks if your data fit into RAM, right? So literally Spark has taken over, at least in some companies, if not all the companies. Spark has taken over primarily because our RAM sizes have grown dramatically. Okay, so this is the history and reasoning on why we have Hadoop, Spark, what happened to traditional databases, all of that stuff, right? So just give me a couple of minutes of quick water break. Just give me a second. Okay, so any questions here? What were the drawbacks of Apache Mahute? So the problem with Apache Mahute was uh, that fundamentally Hadoop was not designed for iterative tasks like gradient descent. It didn't work, unfortunately, right? Because it was not designed for it. If you're storing data to disk every time, again loading the data from disk to your RAM and then to CPU, it was just taking too much time. It was not a problem of Mahute, it was a problem of Hadoop infrastructure. That's because RAM sizes have grown, but Hadoop hasn't changed. When Hadoop was designed, RAM was small, right? So the world has changed, but Hadoop hasn't changed. That's why Spark came into existence, right? So if PostgreSQL is open source, then why didn't it get included in college time? You should ask your college dude. I mean, I don't know. But as compared to PostgreSQL, in our course we chose MySQL because MySQL is much more popular, right? And that's why. So we will not be doing a deep session into AWS. Somebody was asking about how to start AWS. Probably we'll do another session on that for sure. I would like to show you how to run AWS, GCP, all of those things. I've not used GCP and Amazon Azure myself, but I've used AWS extensively. Probably we'll do a live session on that in the future. Somebody was asking about data warehousing, right? So see, what is data warehousing? It's just large amounts of data. A typical database was more like you would access this data more often. Data warehouse is like you're sitting on large amounts of data. A lot of it you may not use on day-to-day basis. So most of data warehousing is built on top of traditional databases, right? Today, obviously, Hadoop and Spark are used extensively for data warehousing. Is it advisable to learn Hadoop and Spark or just Spark? I mean, if you have to pick one of them, I would say Spark today. How do you train a model on 100 GB of data? Actually, depends on, do you really want to train a model on 100 GB of data? Or can you sample the data and get away with it? That's another important question, right? Can you just get away? I mean, can you just sample the data and get a good performance? Why even try to do it on 100 GB of data? If you still have to do on 100 GB of data, you can do it on a single box with 100 GB of data. I think we have a case study, right, on which we do it on tens of GB of data. Of course, it will take you some time. You have to be careful. But you can do 100 GB data training on a traditional laptop, desktop, if you have decent amount of RAM. If you do not have decent amount of RAM, then you'll have to do it in Spark. Okay, sounds good. No, Spark is not like Redis. So somebody is asking, is Spark like Redis? No, Spark is not like Redis, because Redis is basically a hash table. What is Redis? Redis is basically a key value lookup. We all learned about hash tables in the Python section, right? Redis is basically a glorified, distributed, it's basically a distributed hash table. Spark is not. Spark is a compute engine and a file system. Very different things. Pandas, SciPy, or TensorFlow. That's a crazy comparison. Please don't do that. Pandas is for loading data. SciPy is for all scientific operations in Python. TensorFlow is for deep learning. It's like asking, are oranges healthy or apples healthy? Come on. It's unfair to compare them, right? So you have to learn. If you want to be in machine learning, you have to learn Pandas, SciPy, and TensorFlow. That's why we cover all of them in the course. Okay. Where are we? Yes. Okay. So now let's go into distributed deep learning. Again, some of this content we have covered in the course, so I'll go slightly faster here, just in the interest of time. So one thing that happened while all these things were happening in 1999, there was this company called NVIDIA that started out of Stanford, okay, heart of Silicon Valley. And they started something called as graphic processors. They realized that what if, see, you have your CPU, right? You have your CPU and all of that. Okay, you have your RAM, right? You also have your hard disk drive, all of that you have. They said, what if there is a dedicated processor called a GPU, graphic processing unit? What they said, what if there is a special purpose processor called a GPU sitting right next to your CPU on the motherboard, which will take care of all the graphics processing. What are graphics processing? If you're playing games are like heavy graphics work, right? Or if you're doing like movies, if you're doing movie scene editing, right? Or if you're processing videos, that's all graphics intensive. Similarly, if you have a powerful desktop, if you have a powerful desktop with vector graphics for scientific computing, right? All of this were graphics. So NVIDIA started primarily to cater to the gaming market, which was starting off in the late 90s. So people wanted to play games on their desktops. So NVIDIA realized that if I have a special purpose graphics processor, right, that would be terrific, because now I can sell this to all the gamers. And gaming is a multi-billion-dollar industry. So NVIDIA became very popular in the gaming circles for creating something called as graphic processing units. In 2007, they did something very interesting. They launched a toolbox called as CUDA. Okay. So what CUDA is basically a software package. CUDA is basically a software package. What it enabled was, it enabled people to use this GPU, because GPU is a special purpose. See what happens in your CPU. Again, we discussed in the course. A CPU has 4 cores, and CPU has some RAM that it has access to. This is what this is how CPUs work, and your CPUs typically work at a few gigahertz, like 1.8 gigahertz speed. What is a gigahertz? That means it's clock speed. It runs very fast. On the other hand, your GPUs work differently. GPUs today have thousands of cores, and they have one RAM. They have one RAM called VRAM that all of them share, right? So they have lots of smaller cores, right? So a GPU, this is your typical CPU. On the other hand, a GPU has thousands of cores. Each of these cores is not powerful. Here, each of your cores are very powerful cores, right? Here, each of your cores are not powerful. They're not also very fast as compared to your CPU cores. These are actually slow, but there are more of them, right? There are many, many more of them. And all of them can access one RAM called as video RAM. So the big advantage of GPU is it could do vector operations. If I have 2 vectors, let's assume I have 2 vectors. If I want to add 2 vectors, in a typical CPU, what do? I run a for loop. First, I add these 2, then I add these 2, then I add these 2, then I add these 2. I add element by element in a CPU. In a GPU, because I have so many processors or so many cores inbuilt, I could literally sum up these 2. While summing up these 2 on one core, right, I could sum up these 2 on the other core. I could sum up these 2 on the third core. I could sum up these 2 on the fourth core. I could sum up these 2 on the fifth core. Because I have thousands of cores, I can add arrays which are of length 1000 very easily. So what GPUs gave me was, it gave me thousands of small slow cores, but it gave me huge amount of parallelization. See, while adding this on one core, if I'm also adding this on the second core, I'm parallelly processing all of this data, right? In a nutshell. So what GPUs gave me is a huge amount of parallel programming power in my desktop. It gave me a huge amount of parallel programming power on my desktop. And CUDA was a software library that NVIDIA launched in 2007, so that anybody who learns the CUDA software packages could write code leveraging the GPU. So if I want to add 2 vectors, I could do it using CUDA very easily. In 10 lines of code, I could do it. They launched this in 2007. They got lucky. Okay, because in 2007, your deep learning started exploding, right? So it could do vector or array operations simultaneously, and you have distributed VRAM. In 2009, a big change happened. So CUDA was launched in 2007. In 2009, a very big sea change happened in deep learning. And deep learning started off around 2006. It actually took off only after 2012. But there is one cornerstone event in 2009. Rajat Raina, who was a research student of Andrew Ng at Stanford, they wrote this terrific paper where they said, we can build deep learning algorithms faster using graphic processing units, and CUDA, because CUDA was available from 2007. So CUDA became available at the right time for the right problem of deep learning. right? Today, one of the biggest applications of NVIDIA stock went through the roof because of deep learning. Because of deep learning and because of tons of applications of deep learning, like autonomous cars, right? NVIDIA never imagined that they would be building autonomous cars themselves, right? But because NVIDIA made CUDA available and researchers started using NVIDIA from 2009 onwards, people said the best toolkit for deep learning is NVIDIA's CUDA and NVIDIA's GPUs. So GPUs became a default standard for all of computing, especially in deep learning. Again, we have discussed some of these topics in more detail in the course. So then TensorFlow was announced in 2015. There are, of course, alternatives to TensorFlow before 2015, but TensorFlow was super well designed by Google, again, by Jeff Dean at Google and his team, of course, right? So TensorFlow is what Google started building for deep learning internally. So what TensorFlow did was, TensorFlow started making these two things very popular. They said, in a single box, okay, so let's see, actually multi-GPU box. Let me show you a multi-GPU box. Okay, let's see a multi-GPU box. Okay, how does it look? Okay, yes, so this is how it looks. Okay, this is a good diagram. Okay, so but these are Pascal architectures. Okay, just give me a second, I'll show you. Okay, so look at this. This is your motherboard, right? This is your motherboard. Okay, so here you have 4 graphics cards, all connected to the same motherboard here, right? So what you have here is, you could connect, so each of them is actually a GPU. Each of them is a GPU. There is, of course, CPU internally. There is CPU inside this, which I cannot show you here, right? So what happened was, you start getting new motherboards also now, which could take multiple GPUs on the same box. And TensorFlow modified their code to accommodate processing across multiple GPUs. So you have GPU 1, you have GPU 2, right? You have GPU 3, you have GPU 4, all connected to the same motherboard. So TensorFlow modified their code slightly, I think in Jan or Feb of 2016, where they said if you have multiple GPUs on a same motherboard, TensorFlow will distribute the workload across all 4 of them and speed up the whole thing. Then they said, okay, why should we stop here? What if I have a cluster of boxes? What if I have a cluster in a data center? I have a cluster of boxes, the way we have seen the Google's cluster, right? So there are 4 GPUs on this. There are 4 more GPUs on this, right? There are 4 more GPUs. There are 4 more GPUs on this, and so on and so forth. All of them are interconnected using extremely high speed LAN, right? All of them are interconnected using, let's say, 1 GB or 10 Gbps LANs, or Ethernet, basically. So they said, even if you have a multi-GPU cluster where there are multiple motherboards like this, all connected through extremely fast Ethernet, right? Even then TensorFlow works today. So today, if you were to do, so today, most supercomputers of today actually use an NVIDIA GPU. The old school of IBM supercomputers is almost gone now. So because GPUs enable you to get they can do a lot of compute intense tasks. So now what happens is, if I want to do super compute intense, I basically use a multi-GPU cluster, right? And I can do the whole thing on Spark. So I can install Spark also on the same cluster, because there are CPUs also there, right? So Spark can handle both CPUs and GPUs today, right? So you can actually have TensorFlow on Spark, which can do both data intensive and compute intense tasks. That's the world that we have reached now. Very interesting world. Okay, so all of the supercomputers today are NVIDIA graphics based, more or less. Now let's take a simple detour. Since we have 20 minutes, I'll try to cover some of this at a high level. If we miss anything, we'll certainly cover them in the future sessions. Okay. Sorry, just give me a second. Okay. So there is another big change that's happening. So your traditional databases, your traditional relational databases, were trying to minimize the disk space to store using normalization. We discussed this. But then from the early 2000s, people needed special purpose databases. For example, let me give you an example. No. So imagine if I have, okay, let's give this example, right? Imagine I want to verify your, okay, let me change the color here. Suppose I want to verify your login credentials. Suppose I want to verify your login credentials. Okay, you give me an email address, and a password, right? I want to verify if this email address and password exists in my database. If so, I'll grant you access. Now let's assume you have to do this at Google scale with billions of users, or at Facebook scale, or at Amazon scale with hundreds of millions of customers. Right? You want to do this very fast, and you want to do this very, very fast. What do you do? So there is one way. One way is store this in a traditional database. You have your email, you have your password, all of this in your traditional database. That's one way of storing it. Again, there is something called as B+ trees and indexing for traditional databases that I'm not going into. But traditional databases, to fetch this data, will be slower than, imagine if I had a hash table. We discussed what is a hash table in Python sections of our videos, right? In the course videos. Imagine if you had a hash table, let's say. What does a hash table do? Hash table can search very, very fast. Hash table can search very, very fast because you give it a key, it will find the value. It stores internally using some mathematics. So imagine if I want to verify your login credentials at Google or Facebook or Amazon scale at very, very fast speed. Should I use a database or should I use a hash table? Obviously, I should use a hash table. Hash table is super fast. But the problem is with hash table, imagine if I have 100 million customers, this whole data may not fit into memory. This whole data may not fit into my RAM. Then what do you do? Right? So to solve all of these problems, then they said, okay, what if instead of using one box, I use 3 boxes? Again, we have discussed this in the course videos. Imagine instead of using one box, I use 3 boxes, and given any request, I will decide which box it has to go into. Let's assume all the usernames starting from A to C or A to D are here. All the usernames from E to K are here. From L to Z are here, right? So all the usernames from A to D are stored in this RAM. All the usernames from E to K are stored in this RAM. All the usernames from L to Z are stored in this RAM. So this is called as a load balancer. This is called as a load balancer. You can think of it like a load balancer. Okay. So a user comes in. First, I check whether the first character of the username is A, is between A to D, E to K, or L to Z. If it is from A to K, I'll go into this machine. In this machine's RAM, I have a hash table. I'll just check if this username and password is present in my hash table or not. This is called as a distributed hash table, because instead of having one hash table, I'm storing the data in 3 hash tables. Right? So this is called a distributed hash table. So people said, instead of using a standard relational database, I'm better off using a distributed hash table to do this task. I'm better off using a distributed hash table. And one such distributed hash table is called Redis. So Redis and Memcache are basically 2 softwares which basically provide you distributed hash table. That's it. Right? So these are called NoSQL databases. This is one example of NoSQL databases. What is a NoSQL database? It is something which is not a relational database. Of course, your Redis and Memcache cannot do other things that your traditional databases do very well, but they're very good for quick lookups like hash tables. Right? So what happened from the early 2000s is people said, while the traditional databases have served us very well, there is a need for special purpose databases for special situations. For example, what we have is for simple login, right? Which is a distributed key value store. People said having a distributed hash table is a very good idea. So that's how your 2 softwares called Redis and Memcache came into existence. Similarly, there is a lot of text data being stored because internet documents are text documents, right? Okay. So then people said, okay, for text documents, can I create a new special purpose database? And they created something called as MongoDB. And to search text documents better, right? They created something called as Elasticsearch. So there are tons of NoSQL databases, each of them. So there's something called as Columnar Stores. Again, I provided some link to this for you. Okay, because it's a big topic in itself. But if you just go to this Wikipedia page, it explains you why we need Columnar Stores and all of that. So there are so many applications where traditional databases are not optimized for, because traditional databases or relational databases are optimized for disk space minimization. But today, because of the applications of databases have changed a lot, we want special purpose databases for text documents. We want special purpose data stores or databases for distributed in-memory lookups. We want special databases for columnar stores. We want special databases for graph data. Imagine if I'm Facebook, I have a huge graph, right? I have a huge graph like this. What is a graph here? Again, we discussed this in our Facebook case study, right? Each node here is a user. Each of this is a user. If two users are friends, there is an edge connected like this. There are lots of operations that you need to perform on things like this. So these are called as graph databases, right? So for each type of data, there are new NoSQL databases that are popping up every day. There are hundreds of NoSQL databases today. Okay, each specific for its own purpose. Each of them have their own purpose. Okay, so since we are short of time, I'll just cover cloud computing briefly, and probably we'll have a full-fledged session later on, right? Just on cloud computing. So while all of these things happening, there is another big wave that was happening. Again, pioneered here not by Google, but by Amazon. Okay, for a change. So Amazon in 2002 announced something called as Amazon Web Services. In a nutshell, what is the Amazon Web Services? In a nutshell, suppose if I want to lease a computer for a while. Imagine I don't want to buy a computer. Imagine I want to get a computer. Suppose I want to lease a computer. Let's say I want a computer which is 256 GB of RAM for some task, or I want a computer with, let's say, 8 GB of video RAM with GPU, with a powerful GPU. Let's assume I want a box like this to run some machine learning model. I don't want to buy it because this will be super expensive, right? Suppose if I just want to lease a box, maybe for 1 hour or for 1 day or for 1 month. What Amazon said was, Amazon was already selling tons of stuff on e-commerce, right? They were selling millions of books by 2002. They said, along with books, what if we lease computer infrastructure? This is computer infrastructure, right? I have tons of boxes in my data warehouses. Sorry, in my data centers. What if I can lease a box for 1 hour or 1 day or one month or 1 week or whatever time period? So even though I don't have a powerful box at my disposal, I can just, so this box is in Amazon warehouse. It's most likely a Linux box. Of course, you can get Windows boxes also today, right? So cloud computing is all about being able to lease this compute infrastructure per unit hour or per unit time, right? So AWS, so there is this thing called EC2. What is EC2? Elastic Compute Cloud. What it provides me is, if I want 10 computers today, if I want a 10 computer Hadoop cluster, I can create a 10 computer Hadoop cluster in AWS in 10 minutes right now. Sorry, just a quick water break there, right? So what Amazon started providing was, Amazon said, I will provide you infrastructure like compute infrastructure as a service. You can lease it from me whenever you want. Very interesting, right? So this was the idea that Amazon pioneered around 2002 when everybody was laughing at them. Today, it is one of the most profitable businesses at Amazon. It's a cornerstone of Amazon's business today. Okay, Amazon is the largest cloud computing player in the world today. And they started this whole thing like almost 17 years back in 2002. So today, using EC2, I can lease 1 box, or I can lease 10 boxes or 100 boxes. And I can lease extremely powerful boxes. Actually, whole of Applied AI course actually runs on an EC2 instance or an EC2 box. We actually lease boxes from Amazon Web Services. Okay, we lease fairly powerful boxes to host all of our content, all of our databases, all of our website, everything on EC2, right? So instead of us buying expensive servers today as a small startup, we are just leasing EC2 resources on monthly basis. Similarly, there is something called as S3. S3 stands for Simple Storage Service. Just the way EC2 is giving me compute power, imagine if I want to store something in the cloud. Okay, imagine if I want to store something, if I have 10 terabytes of data that I want to store somewhere, I can just lease the space from S3 and store 10 terabytes there and pay on monthly basis. So what cloud computing gave us is, it gave us compute infrastructure on demand as and when we wanted. That's how it started. Slowly they said, instead of just giving infrastructure, instead of just giving computers or storage space, why don't I give full-fledged databases as a service? Right? So that's how it started the whole area called platform as a service. Okay, so you hear all of these terms called platform as a service, infrastructure as a service. So today Amazon has something called as Redshift. Okay, also Amazon has standard traditional MySQL databases. So we actually use a MySQL database on Amazon databases to host all of our student data, right? So Amazon, in addition to providing us compute resources, storage resources, also provides us database instances. Why are we using these database instances? Because there is some other admin who is taking care of ensuring that this database doesn't shut down, this database works properly, backing up the database, all of that is taken care by them, right? So this is what cloud computing is in a nutshell, right? Of course, by seeing the success of Amazon, Google, which had a large, extremely large computing infrastructure, said, let us also launch uh, our own cloud computing infrastructure called Google Compute Cloud. Microsoft launched their own thing called Azure in 2010. IBM, Oracle, and ton of other companies today, almost every Tom, Dick, and Harry company has a cloud computing platform today. But the most powerful today are AWS, Google Compute Platform, and Amazon Azure. These are the three most powerful cloud computing platforms. And what they're giving you is they're literally giving, it's like instead of leasing a home, think about it as, or renting a home, think about it as leasing or renting a computer or some disk space, right? The most important lesson of today is the whole landscape is constantly changing. Remember, I started my career in 2009 during the heydays of Hadoop. Okay, most NoSQL databases were not existing in those days. Most NoSQL, like we built our own key value store when I was at Amazon, or at least the software engineering team, and I used it. I didn't build it myself, right? But when I moved to Amazon, while we were building some infrastructure at Amazon, we just used Redis because it is already readily available, right? So within the last 10 years that I've been seeing this, huge changes have happened because of multiple things. Number one, disk space became extremely cheap, significantly cheaper than even previously. Initially, we used to have hard disk drives. Now, solid state drives have become popular. Solid state drives are much, much faster than hard disk drives. So this is one major change these are all technological changes. Similarly, the amount of RAM that's available has increased dramatically over the last 10 years. Similarly, the cost of cloud compute has become very cheap now. GPUs are becoming very cheap today, right? So every 5-6 years, because of these fundamental foundational changes, the whole landscape of technologies will change, because your hard disk could get faster, your RAM could be cheaper, because your compute is becoming more affordable. It could be changes in CPU, GPU, RAM, storage, whatever it is. These technologies will keep evolving. So if you ever want to be good at big data technologies, don't get stuck to one technology. Keep learning new things. There is no replacement for it. If I did not learn Spark, and if I said, yeah, I knew Hadoop, I'm very good at Hadoop, I won't learn Spark, I would be a dinosaur in the machine learning community, or at least large scale machine learning community, because a lot of machine learning guys have moved to Spark today, right? Most of large scale implementations, not of machine learning, but production environments. Again, I learned all of NoSQL databases by working with my software engineers in my teams, right? Because I was not responsible for many of the software stuff. I learned a lot of cloud computing. I learned a lot of NoSQL databases from the software engineers that I was working with closely. These were people who are like extremely senior people to extremely young folks. Okay, I learned most of these technologies, why they are needed, how they are needed, how to use them, why they even exist, right? All of them by working with software engineers. Of course, because as a machine learning guy, I was not even Hadoop and Spark I learned because of software engineers that I worked with extensively, right? And you need to constantly learn these new things. There is no end to it. Okay, I think there is a big joke that many of our elders tell us, that okay, study well till 10th class, your life is settled. Then they tell you, study well till 12th class, your life is settled. Get into an IIT, your life is settled. Then if you get into a good engineering college, tell you, okay, get a good job, your life is settled. This is all crap. I'm sorry to use that word. The day you stop learning, let's assume you stop learning Suppose you join a job, after 2 years, you stop learning. Within 5 years, I don't care whether you're from Stanford or MIT or IIT. You're a dinosaur because you have not learned. You stop learning constantly, your game is up. So I think what our elders have told us that 10th class tak thoda pad lo, or study till 10th class. Those of you who don't understand Hindi, study well till 10th class, you're done. Study till 12th class, you're done. You are never done. The day you stop studying, within 3-4 years, you're a dinosaur. Your life will saturate, your career will saturate. This is an honest viewpoint. I have seen brilliant folks who are my classmates at Indian Institute of Science, which is considered India's best institute for higher education, who are not growing today because they stopped learning. I've seen brilliant PhD students from Stanford who didn't progress in their career because they stopped learning. The day you stop learning, your game is up. Or at least if you stop learning for 2 to 3 years, your game is up, because you're now behind the world. Some other younger kid would have worked hard and learned, and who would beat you. So in the long run of career, you have to constantly evolve and change to the landscape of technologies that evolve and change. The moment you stop, your game is up. It's as simple as that. Okay. Having said that, let's go to the comment section a little and see. Since we have 5 more minutes, I'll try to answer a few of them. Okay. RAM size, hard disk size for Spark and big data. See, obviously, if you have more RAM, right? If you have more RAM, obviously your computer will work better, because you can do more iterative tasks. Because, of course, if you have more hard disk space, you would require fewer boxes. See, all these are trade-offs. Obviously, if you have larger RAMs, Spark would work better because it can store more intermediate data in the RAM instead of storing it hard disk, which means it will be faster, right? So, hey guys, my Hindi is bad. Trust me. I studied in Dehradun in a military school for 5 years, but I've not learned much Hindi and I've forgotten most of it. So please bear with me. My Hindi is bad. So sorry. Sorry, I'm not an expert on Bitcoin to comment at this stage. Yeah, you can use Spark instead of SQL in machine learning. What do you mean? So for data pre-processing, if you want to use a Spark, yes, you can use, you can use any tool that works in your case. So if you want to use native Spark code, you want to write code in Scala, be my guest. Please write it in Scala. But it's faster to write it in Spark SQL or something like that, right? So this is a very good question. In today's scenario, where would Hadoop still be used over Spark? Very good question. So the good thing with Hadoop is you don't require large amounts of RAM for it to work well. So if you have tasks where you're not worried about speed, and if you have large amounts of data that you want to constantly crunch, right, like an offline processing job, right, Hadoop is still better because you can get away with cheaper hardware. You don't require like 10 GB of RAM or 16 GB of RAM. So having a Hadoop instance, see, if latency is not a constraint for you, and if you don't want to do iterative compute intensive tasks, you want to do only data intensive tasks, Hadoop is still a good option today, because Hadoop itself is changing. The newer versions of Hadoop also give you a lot of new advantages. So Hadoop is still good if you have if you want to run some offline jobs with no latency constraints, because you can get away with cheaper hardware, right? So your cost will reduce, but your performance would still remain the same. So C++ is known to be performance intensive if coded properly. Is there any demand for C++ or machine learning in India for experienced developers? See, I think we discussed this in the course also in the miscellaneous section of the videos, that if you really have latency requirements, for example, if you have to run some code on a mobile phone, right, you are better off implementing it in C++ because it's going to be more performance. It's going to give you better performance in a nutshell, right? So today, even Python libraries, a lot of libraries internally use, like TensorFlow is written in C++. While it has a Python interface, you can write code in Python. The whole core code actually executes in C++ for speed. So there are certainly some roles where people are looking for C++, but Python and R are more extensively used. Why don't computers shift to GPUs completely? I wish GPUs are cheaper. GPUs are not at all cheap. When GPUs and CPUs are of same cost, probably we'll see more GPUs on our laptops and desktops. And again, remember that GPUs are each core in a GPU is not optimized for each core is not optimized for general purpose tasks. So the CPU core is designed for general purpose tasks, whether it's word processing, whether it's your Skype chat, it's designed for general purpose. while GPU cores are designed for vector operations, right? So that's why you don't see GPUs as often. Is SSD treated as RAM or hard disk? SSD is treated as a disk by Hadoop and Spark. It's not treated as RAM. It's not. Do we need to learn separately and switch on to PySpark, or we learn PySpark directly in Python? PySpark you can learn in Python itself. Why worry about it? PySpark is basically a bunch of, think of it like learning a new library, right? Now you have some idea of what Spark is. It is like simply learning a new library in Python. That's it. Kafka is high volume. Yes, Kafka is again. There are tons of NoSQL and real time or high volume processing engines. Kafka is one of them, certainly. Comparing Dask with Spark. Okay, this is a good question. I think Spark is more popular. Dask hasn't yet gained that much popularity. And yeah, so not yet. There are some, I think Dask is more useful for, again, by the way, I have not learned Dask in full detail myself, but from what I recall, Dask is better for graph databases, if I'm not wrong. So where do you learn from PySpark? Just Google search PySpark tutorial. You'll get hundreds of tutorials. It's straightforward sitting there. So that's not a problem. Again, I'll give you links for Spark MLlib, where you can write code in Java, Scala, or Python. As far as machine learning is concerned, I'll give you some links. You can just use that. At the end of this session, I'll post some links on this channel itself, and let's see. Yeah, you can set up Spark on your laptop. Of course, it's going to be a single box. It's very easy to set it up. You can make it work. It's not at all hard. Of course, you won't get the performance increase because you're still operating in a single box environment. Okay. Where are we? Okay, can I set up Spark? Yes. Some pointers on streaming data, please. Yeah, streaming data is another beast in itself. Yeah, you can do, by the way, you can do streaming data in Spark also. There is something called as Spark streaming, on which you can do some of it. The difference between micro server and EC2. Guys, EC2 is basically a system that gives you computers, or that through which you can lease computers, right? A micro instance is the simplest and the cheapest instance on EC2. I think it has some 2 GB of RAM and stuff like that. On EC2, you can rent lots of boxes. You can rent, I think, boxes up to almost 256 GB of RAM today, or probably even more. I think there is even 512 GB of RAM boxes. So a micro instance is basically the simplest one. Could you please suggest which one is better, Scala, Java, or Python? I would still say Python because it's useful in more places. But if you really want to do Spark programming internally, Scala is certainly a good option. But if you're doing it mostly for machine learning tasks, it doesn't matter, because the code that you write in Python in Spark anyway gets converted to Scala code internally, gets executed. So how organizations are adopting to AWS, cost and security aspects. Dude, one of the world's largest companies called Amazon runs on AWS. So you can, and they have security, like world-class security. They have 200 million customer data, right? So don't worry about it. If Amazon is running, Amazon wanted to prove to the world that you can run one of the largest internet companies in the world on AWS. That's why they moved a lot of their workloads to AWS. I think almost all of it to AWS. There was an internal memo that all of us have to move to AWS eventually. So you better design, because we wanted to prove to the world that AWS works for one of the largest internet companies. If one of the largest internet companies with so much of customer data can run on AWS, I think every major organization can. Do we need to be skilled in Spark to get a job in ML? Again, different companies have different requirements. There is no end to what companies can ask. Companies can ask you to be a rocket scientist, can ask you to do everything. But to be honest, when at least I used to hire, or teams that I know used to hire, they used to say, if you don't know Spark, that's okay, but you should be willing to learn once you join. If you know basics of programming, like I have hired, I think almost every person that I've hired for my teams, or at least I shouldn't say not every person, almost 90% of people that I've hired did not know Hadoop or Spark when they joined my teams as machine learning engineers. But they ended up picking them up in a few weeks, right? So you can pick up these things. So that's not a problem. Okay, folks, I think we have run out of time. I'll share. So let me just get it. Okay. Okay. 1 second. Where is my mouse here? Just a second. Okay. Okay, I think we have run out of time today. So thanks for joining us. This was only an introductory overview session on big data technologies. I just wanted to give you a historical perspective and where is what and how is each of these techniques needed. We'll certainly do more sessions. We have many more sessions coming ahead for us. And yeah, we'll cover probably AWS in one session. We'll try to do as many as possible. Again, we don't want to divert too much away from machine learning because we don't want to do a big data course right away, because that requires us to do more fundamental stuff. So we will try and balance between both. We don't want to go too deep into big data alone by missing out the machine learning components, but we'll try and give you whatever tools you need to be a better machine learning engineer. Okay, sounds good, folks. Thank you very much for joining us today. I'll share the notes for this discussion on the miscellaneous thread on our sorry, I'm almost losing it now. So I'll anyway share it in our I'll also share it on our Slack groups. Okay, thank you for joining us. I think been a hectic 2 hours for me also. Thank you for joining once again. See you again. We'll announce the next live session. Actually, since we thought we'll do 70 plus hours of live sessions every year, we were thinking about doing 2 live sessions every 3 weeks. That's the rough pace that we will do, because we have roughly 52 weeks in a year. So if we do 2 live sessions every 3 weeks, we would end up with roughly 35 36 live sessions. That's about 70 hours of live session. That's what we are thinking. Again, we'll modulate, we'll speed up, slow down based on student requests, based on demand stuff, based on changes on our website and stuff like that. Hopefully we'll have the new website up and running soon. We are just working tirelessly on it. The whole team is sitting on it now. And thank you for joining, and suggest us more topics for future sessions of live sessions like this. And see you soon. Thank you. Bye bye.